You like our sign? We like it so much we made it this year's t-shirt. Those are fluorescent light tubes. At home in your electrical fixtures, you turn on the power, a strong electric field is generated. The gas molecules inside those tubes become excited. When they drop back down to their lower energy state, the energy they give off causes the tube to fluoresce or give off light. Here they're not hooked up to anything electrically, they're just tied onto a piece of wood. We use a Tesla coil to generate that strong electric field. In fact, the electric field is so strong around the Tesla coil, the air breaks down and becomes a conductor. That's what those big sparks are, and that's what lightning is. So we made a little bit of lightning today. Welcome to the Physics Show. The community around Foothill College is so supportive of the college. We appreciate it very much. We're delighted we could put a show like this on for you. I'd like to start off by asking you a question. If this is your first time to a physics show, give yourselves a round of applause. All right, welcome. And if you've been to one or more shows in the past, give yourselves a round of applause. Welcome back. And this is the Physics Show, so I have to tell you what physics is, right? What is physics all about? Well, when you're in school, you learn all kinds of wonderful things. You can almost take the things that you learn and put them into different categories. You've got your reading and writing and your history and your math. And one of those categories is science, right? Yeah, give it up for science, yeah. And under science, there's so many great things. We put those into different categories. We've got our biology and our geology and our chemistry. And one of those categories is physics. And physics tries to explain the world we live in. How does the world work? It tries to explain the world we live in. And because of that, there are lots of topics even under physics. Today we're going to talk about light, sound, and temperature. Maybe next year, I don't know, maybe inertia, maybe electricity and magnetism, we have to decide. But I like to say physics is a journey, and we're delighted you're coming along with us on that journey. Let me introduce the folks that are presenting today. We're missing my colleague, David Marasco, today. He is at a national physics teacher meeting. I bet you wish you could be there. Well, David is taking one for the team, and he's representing Northern California physics teachers. But we do have one of our students on stage here, Kimmy Long. And I'm Frank Coscarano. And you know what I say, if you can't have fun with physics, you aren't a very fun person. So let's get started, let's have some fun. We're going to start out by talking about light. Now, the electromagnetic spectrum is all the different forms of light. Get the next slide. Is it stuck? So light is part of the electromagnetic spectrum, which you will see in just a second. And the electromagnetic spectrum is made up of we give things all different names. I'm not sure why we do that, but it's all really the same stuff. Radio waves that make our radios work, in the car maybe. Microwaves that make your microwave ovens work. Infrared, if you watch a movie about the military, then they're wearing those night vision goggles. Those are looking in the infrared part of the spectrum. And if there are some animals that sleep during the day and come out at night, and their eyes are tuned to infrared, to the infrared part of the spectrum, they can see that stuff too. But we can't see that. Our eyes can't see any of this stuff. Radio waves, microwaves, infrared. Our eyes can't see any of that. It's not tuned to that. But we can see light from the sun. Visible light, we call it, because our eyes are tuned to that. And of course, light from the sun can be broken up into all the colors of the rainbow. And then on the other side, there's ultraviolet. That's the stuff that gives us sunburns and X-rays. It's all the same stuff. We just give it different names. But all of it has this property that it changes speed when it goes from one medium to another. So if a light is coming along at an angle like this, part of it, if it had some width to it, part of it hits the slower material and slows down, and part still goes fast, so the direction changes. And when it comes out the other side, part speeds up while the other part's still going slow, so the direction changes. And this change in direction when a light travels from one medium to another is called refraction. Now, it gives us the ability to do some interesting things. But let me see if I can demonstrate this for you first. So I've got a piece of plastic, and we're going to send some light in, and we'll turn the lights down, and you'll see that the light that comes in, if it comes in straight, perpendicular to the surface, it just goes straight through. There's no change in direction. But if we bring it in at an angle, if we bring it in at an angle, where it hits the interface there, that's where my glass is, where it hits the interface, the angle changes, the direction changes. You see how it changes direction slightly there? And where it comes out, here's my other side, where it comes out, the direction changes again. So that is refraction. And it gives us the ability to focus light. So let's take a look at this. This is a model of the human eye. And this eye is missing something. It's missing its lens. So the light just comes straight through without being focused. And this, back here at the back of our eye, that's where our receptors are. That's where the light needs to be focused. That's how we see. And this would just be a really blurry image. You wouldn't be able to make anything out. Luckily, our eye has a lens. I'm going to slide that lens in there. And so the light, when it goes through the lens, it focuses right there. Where is that? Well, that's where our receptors are. That's where we need to be able to see a nice sharp image. This eye is working properly. But sometimes our eyes don't work properly. So this eye, the light's focusing here, but where are our receptors? They're back here. This would be a blurry image. This eye is not seeing properly. This is a blurry image. Luckily, we can make glasses because we know about refraction. And we slide our glasses on, and the focus is right where it's supposed to be. This eye now can see a nice sharp image. Take our glasses off, and the focus is in the wrong place. Put our glasses on, and we can see a nice sharp image. Now this works for other things, not just glasses, but anytime we want to focus light, a telescope, a camera, a magnifying glass, anytime we want to focus light, refraction is this property that we're using that enables us to do that. Now, what I've been talking about so far is light moving from the fast side, maybe air, into the slow side, maybe glass. But it could go the other way around. Actually, we saw that earlier too. It could start out in the glass and try to come out. And it also bends, takes a different path. But the interesting thing about this situation is there comes a special angle where that light can't escape. All of the light is reflected back in. That's called total internal reflection. So let me show you that with this plastic spiral. And what I'm going to do, I'm going to shine a light in this straight edge here, in the straight side. And I'm going to point the light up towards the top. You see it trying to get out? It can't get out. It bounces back down. Now I'm going to point it down towards the bottom. It can't get out. Point it up towards the top. Point it towards the bottom. It can't get out. But if you look at the center of the spiral, pointing at the camera, that's the bright spot in the center of the spiral. That's finally where the light can make it out. That's total internal reflection. Now Kimmy's going to show us a demonstration involving total internal reflection.
So Frank just taught us about total internal reflection using that plexiglass spiral shape. Well, here we have this contraption we built to demonstrate how this property also works with a stream of water. We have the main chamber here we plan to fill with water. Currently it's empty. On this end, we have on one side a clear glass panel for us to shine light into, and a hole on the other end for the light to shine out of. So we'll test that right now, make sure it works. And it does. Some of you may be able to see it over here, or if we can get it on the screen, you can see it there on my hand. That's my hand. So the light shines through, everything works. Now let's see what happens when we add water to the system. So notice how the light is completely trapped in the stream of water and it fills the body of water below. And that is total internal reflection with a stream of water.
So we told you earlier that all those different parts of the electromagnetic spectrum are really the same stuff, right? Radio waves, microwaves, visible light, it's really the same stuff. It's just that our eyes can only see parts of the spectrum. So you know that we can send information over radio waves, right? It carries information to your radio, maybe in your car. And there are two ways to do that. There's FM, that stands for frequency modulation, and AM, that stands for amplitude modulation. And so we decided we would want to show you that you could do the same thing with light. So on the other side of the stage, we have a laser. And we're going to, we made a circuit that takes the output from a music output from a cell phone and puts it on top of this laser beam the same way your AM radio works. So Kimmy's going to set up her phone so it's playing some music, and she's going to plug it into the input on that laser. But first we want to show you the laser beam while we get it dialed in at our receiver on the other side. So it's coming over here to this mirror, and then it's coming over here, and on this side we have a receiver. And now's the time where we would steal the art from the museum, right? Okay, so Kimmy's going to hook up her music player.
Our whole universe was in a hot, dense state that nearly 14 million years ago.
So we can hear the sound. How do you know it's coming across this laser beam? Let's cut the beam.
History all started with a Big Bang. The dawn of man is really...
Okay, so we can send information over a laser beam the same way we do over radio waves. Now Kimmy is going to show us a neat application of that.
Okay, so now that we understand total internal reflection and transmitting information across a laser, let's discuss how we use this in our everyday lives. So, who here has ever wondered how you can connect with friends over the internet almost instantly, say through FaceTime or Fortnite? Yeah, okay. Well, some of the highest internet speed connection today is thanks to the invention of fiber optic cables. So, here we have a fiber optic cable that consists of a bunch of really thin plastic or glass wires that act sort of like our plexiglass or our stream of water. So when we shine light into one end, carrying information, it totally internally reflects throughout the cable and comes out of the other end as information. Okay, it's very faint, so you have to look close, and most of you will probably only see it on the screen there. But you can see the light does make it through to the other side, and this works no matter how we bend or move the cable, or even how long it is. All right, and those are fiber optic cables.
So another interesting property of light is that it can pass through some materials, but not through others. So when the light hits the windows of your house, it passes through them. We say they are transparent. And light passes through the windows because the atoms and molecules that make up your windows cannot absorb the exact energy that the light's carrying, so the light goes through. But when light hits the walls of your house, it can't get through. We say they're opaque because the atoms and molecules can absorb the exact energy the light's carrying, and so it absorbs the light, it can't make it through. Now we're going to take a little bit of a look here at opaque and transparent in different parts of the spectrum. So I have a heater here, I'm going to plug it in. This wire is the same type of wire that's in your toaster at home. We run an electrical current through it, and it heats up. So I just plugged it in, and it's going to start to warm up now. And first, it's going to start to glow in the infrared part of the spectrum, and if I put my hands around it, I can feel the heat coming off. I can feel the infrared. So my skin is seeing in the infrared part of the spectrum, but our eyes can't see that. But if we wait a little bit longer, it'll start to get hotter and hotter, and it'll start to glow in the visible. It'll give off red light. It'll be red hot. Okay, so we've been talking about, we happen to have an infrared camera here. So the camera can see in the infrared, and that's the heating element there. All right, so we've been talking about infrared and visible light.